The math is easy. What are you going to do? Vector u plus vector v. P.S. Remember, I said handwritten notation. I was kind of happening it from my desk. You cannot just write the letters. You have to write the arrows above. True? Oh, I see people writing arrows, and I said it from my desk. Handwritten notation. You cannot just put the whole letters. Vector v, the arrow above. Okay? But the math is super easy. So u plus v, what do you guys get? The resultant vector, the result, or the net change when you add u plus v, you end up with 3/4. As easy as that. How about u minus v? Yeah! 1 negative 2. How about when you do 2u minus 3v? Negative 7. Yeah. Now the graphs get a little trickier. Now, first of all, when we graph vector u, what would my initial point be? What do you guys think? We have to go from an initial to the final, from a tail to the head. Does this notation tell me the initial point? So, well, worst comes to worst, always use the initial point as the origin. And then how do we sketch the 2, 1? And 2 would be horizontal or vertical?
Horizontal.
Good, just the way we're used to. Okay? So, 2, 1, I would go ahead and put the head at the point. Does that make sense? So go right 2, up 1, and put the head right at that spot. There we go. There's vector u. And how do I sketch vector v? Well, think of the origin, the beginning again. I'm going to go right 1 and up 1, 2, 3, right? So then put the head at 1, 3, or pointing to 1, 3, you could think. There we go. And there's vector v. Okay, so I had vector u and I had vector v. Now, graphically, what do these operations do? Mathematically, it's easy if you have the components. Mathematically, it's easy if you have the components, because it's like, oh, just add the x's, add the y's, add the horizontal components and the vertical components, which is all well and good, but what does that actually mean in a vector diagram? Thinking of, once again, the roller coasters, I can see the different forces acting on a certain object. If we're trying to add together, we're trying to see the resultant, or the sum, or the net. So then when you guys wrote 3, 4, how would we sketch it? Well, it'd be 1, 2, 3, and 1, 2, 3, 4. How does that make sense? Well, if I was to go right 3 and up 4, and I was to show this one's resultant, guess what it would be the same thing as? Oh, I need to unhinge them. Hold on. There we go. Now they're unhinged. Let me unhinge all of them real quick. Shoop, shoop. Shoop, shoop. Okay. What's it going to be? The same thing as? That guy with that guy. You can move vectors around because equal vectors have the same length in the same direction, but they don't have to be in the same place. So I can say, hey, u plus v is the same thing as going v and then going u, and you see the resultant. Or another way of looking at it is u plus v. I could have started with u, and then I could have added v. So vector addition can go either way. U plus v is the same thing as v plus u. And so if you put two vectors, head to tail, the head of one to the tail of the other, and follow, in a sense, the flow, even though it's not necessarily what's going on, but follow the flow, you can see the overall resultant. So the resultant, in a sense, is the hypotenuse, but I can't really call it that because is this necessarily a right angle? No. But we can call the resultant the connection between the tail of the first vector and the head of the last. Now, what's going to change, what do you guys think, in letter B when we go to do subtraction? What is subtraction mathematically? Adding the... Well, what does negative mean? Adding the opposite. Adding the opposite. So how could I... Wait, who's opposite or who's negative in this in this operation? Letter B. V is opposite, right? Okay, so if V is opposite, how could I make vector V, the green one, how could I make him opposite? Opposite. Is that going to change the magnitude or the direction? Opposite. Make the arrow what? Go to the right. So when I do U minus V, I need to take vector V, I need to make him opposite. And when I make him opposite, question, how do I connect the vectors now? Well, hold on. We could actually look at the math and say it's going to be 1, negative 2, right? So we could go 1, which I think is what I put this guy as. That's 1, that's 2-ish. Negative 2, I'm going to go ahead and go, well, that's 3. Go down a little bit. Okay. This might be a little bit off. We'll pretend. We can show 1, negative 2, right? How on earth did these two vectors get there? Could I have connected? Yes. But what else could I do? There we go. Or, if I didn't do that, couldn't I have kept it this way? Kept it the old way that we had it originally, just by switching vector V? What happened to the switching this? Switch. Okay. And couldn't I have moved this one up? Would that have also worked? Yeah, that would have also worked. Vectors don't have to stay in the same position. We can shift them around, we can move them around, as long as we keep equal vectors with the same or equal. Vectors will be the same, vectors will be equal, vectors will be equivalent as long as they have the same magnitude and the same direction. So I have to make sure it's going to be parallel. Wherever I move it, keep it the same angle. I need to make sure it keeps the same length. Let's try to visualize the last example, 2u minus 3v. What's going on when I multiply vectors by something? By a scalar is what we would call it. What do you think 2u does, first of all? Makes it longer. Good. Doesn't change the direction, only changes the magnitude. So instead of going this distance, which would be 2 squared plus 1 squared, or root 5, instead of going root 5, how far is it going to go? 2 of those, right? So instead of just going this distance in the same direction, it's going to go twice as far. Do you guys agree? Pretend that was actually in line, though. What's that thing? Distance. Is that a little better? So this is going to be 2u. Okay. So how are we going to do 3v? Multiply his length by 3. What would v's length be, or what is v's length currently? X squared plus y squared is hypotenuse squared, right? So we could say 1 squared plus 3 squared, which would be what? Rad 10. So that rad 10 is going to get multiplied by 3. So instead of just going this 1 unit of its length, it's going to go another unit, and another unit. Okay, so 3v is going to multiply v times 3. Same direction. Okay, so how should I show what's going on? Wait a minute, hold on. Am I adding these two, though? Ooh, I'm subtracting, right? So what does that mean? This guy needs to go the opposite direction, right? Okay, now let's go ahead and look at what our answer is supposed to be. We have 1, negative 7, right? All right, so let's go ahead and figure out negative 7. The way I'm going to figure this out is I know this one is F3, F6, F9. So if that's 9, I'll go ahead and that's 3-ish, that's 6-ish, that's 9-ish. So I can split this into thirds, split this into thirds, and split this into thirds. So So 9, 8, here's 7. Okay. So I can go ahead and take this distance, which would be almost the span of my hand. Carry that down. Almost the span of my hand. So pretty much right here at the very, very bottom. Negative 7. I know that 1 is this distance. Okay. So here's my resultant. 1, negative 7 would go down this way, right? How do I figure out if this is right? Head to tail. Good. Head to tail. So I could move this down, or I could move this up. How do we do? All right. It's a little off, but that's okay. I figured it would be. But if I had done it perfectly, if I had measured it out and the units had been nice and even, should this pretty much match? And the answer would be yes. Okay. So, vector diagrams. That's the graphical representation of what the math is doing. But once again, this is when vectors are given to us in components. Vectors could be given to us like we saw a couple days ago in or with magnitudes and directions, where we have to actually find the lengths and the angles. But if we can get the vectors themselves into component form, the math, let's just say, gets a lot easier. We have 5 more minutes until we'll transition to the test corrections. So we have until 11:15, right? So here we go. You guys don't need to write these down. Let's see if they make sense. Does it make sense that from you seeing me shift things all over the board, that u plus v would be the same thing as v plus u?
Yes.
Yeah. Does it make sense if I add a 0 vector to a u vector, it'll stay the same?
Yes.
Does it make sense if I multiply a vector by 2 and then by 3, it'll be the same thing as multiplying 2 times 3 by the vector? Okay, does it make sense that the vector will the scalar will distribute? So 2 times the sum will be 2 times each of them added together? Okay, so these ones are supposed to make pretty good sense, but what operation do you guys not see happening? I see addition, I see subtraction, I see multiplication of scalars. Don't see division, but if you divide by 2, wouldn't it be the same thing as multiplying by like a half? So maybe some divisions will be okay. I don't see powers, good. And what do powers represent? Repeated multiplication. Do you guys see multiplications of u times v? I see c times u, I see c times d times u, I see little constants, or what we would call scalars, times u and v. But I don't see any vector multiplication, and that's on purpose. It behaves in a very different way. Yeah, go ahead.
Can you go back one to, I think it was number 9. With the C, what is that saying?
This is saying the magnitude of, so vector v, like for instance the one we were doing a second ago, where I had 1, 3, and then I was asking you guys what the magnitude of the length was, and we figured out root 10 from the Pythagorean theorem. This is saying, okay, well, when we did 3 times that v, because it was 2u plus 3v, when we did 3 times that v, the magnitude of that result will be the same thing as the beginning magnitude times the absolute value of the constant. Does that make sense? So let's say we had like negative 2v. What would that magnitude be? We'll find the magnitude of v and then multiply by 2. But remember, the negative has nothing to do with the actual length. It only has to do with direction. Okay. Good question, Andrew. Okay, this page is going to introduce us to one more way of writing a vector. It's not really that much more complicated. Remember, handwritten notation. What do we need for the vectors? Okay. Good. Technically, even for the i's and the j's. Now, these i's and these j's, I just make the arrow the actual points and don't do the point and the arrow. It's up to you as to what you want to do. The i's and j's are not talking about complex numbers, okay? Not talking about complex numbers. Real world examples, real world measurements, no imaginary, sometimes on, sometimes off with like electricity and currents. No, that's not going on here. For our vector notation, we did talk about how we could, first of all, the very first thing we said is that we could express this vector in terms of, technically, his magnitude and direction, which means we could say, hey, this vector has a magnitude of, you guys see where I would get square root of 40? Hold on, except I can't add, so that's okay. It's it's not 40. It would be 49 and 25, which would be 60, 74. Does that sound better? 2 goes into 74 37 times. Ugh, that's not going to simplify. Double check me. 35 and, no, 49. 49 and 25. 69 and 74. Yeah. Magnitude. Direction we'd have to find using tangent inverse of, we'd have to do a triangle, bless you. How we go right 7 and up 5, so that'd be tangent inverse of positive 5 over 7. Opposite over adjacent. So we could express this vector by saying, hey, turn this angle, all right, and then go out this distance, okay. And we would have the overall effect of the vector. Turn this angle, go out this distance. Okay, cool. We also talked about, hey, well, hold on. If we know the legs, can't we just say go over 7 and go up 5? That's kind of a nice, neat way of saying it. But there is one other notation, and it's going to use these standard unit vectors from down below. The other way of writing it is technically called a linear combination, and we'll see some notation for it in just a second. But the linear combination is basically going to say, we can also say 7 times the unit vector I plus 7 times the unit vector j. That's another notation. All 3 of these ways of noting a vector, ultimately, sorry, not 7j, 5j, I apologize. All 3 of these ways of noting vectors ultimately accomplish the exact same thing. The I and the j is just talking about, hey, this little I vector, he's our unit horizontal vector. So he ultimately, well, the I vector just has a little length of 1. And his angle will always be 0 degrees. I guess you could say 0 or 180. Nope, 180 would be going the wrong direction. That would be negative I. Whereas j vector is going to be the unit vertical vector. His length will also, like a unit circle, his length will also be 1, but his angle will instead be 90 degrees, or pi over 2. So there's a special notation for the most basic unit that's going due east or going 0 degrees. And then the unit j vector is going due north or going 90 degrees. And so if you look at our vector up here, the 7 and the 5, as soon as we put it in this linear combination notation, what it does is it doesn't just tell us go right 7, it says go right 7, but like a vector. So go the horizontal vector 7i, and then go the vertical vector 5j. And so what it's really doing is saying, hey, if you did the sum of these two vectors, 7i and 5j, you would have the resultant of v. So it's breaking literally a single vector down into its components, into its horizontal vector and vertical vector. But in the end, or at the end of the day, it's kind of just like a new notation. Hold it.
Where did you get that letter from?
That's notation for magnitude. When we put little double lines around a vector, what that means is the length.
Oh, okay.
Yeah, it's a notation. That's from yesterday's notes, sorry about that. But it just means magnitude. Think double absolute value bars. That's how it was looking at it yesterday. Okay, so if we were doing a problem like this, oh, I basically already did this one. We just did an example. Let's take this example out because we're trying to save time anyway, and I want to finish this page, which I think we can do in like basically a minute. We just did an example like that. So let's go ahead and take this, and let's work an example out. Now pause when you guys are writing this handwritten notation. What are you going to put above all these little guys? Arrows. Little vector arrows. Okay, I got them all. Handwritten notation, because you're not typing. All these little guys are vectors. But kiddos, can you figure out what to do if you see vectors given to you in linear combinations and it says, hey, can you double vector v, please? I'll give you a second. Go ahead and get down v. And linear combination form, get down v. How would you double vector v?
6 i's.
Good.
Minus 4j.
Good. If you need to, you could technically write this little guy and say, hey, isn't this 3 negative 2? And the answer is yeah. You could write it that way. So couldn't I write 6 negative 4 as my 2v? That's true, but they want it as a linear combination, so 6i minus 4j. Ultimately just double both components, just like we saw as far as how easy the math was a moment ago. How about u plus v? What if we were to add them together?
4i plus 3j.
Yep. 4 vector I plus 3 vector j. So is the math any harder? No, just new notation, different notation. Now here's an interesting one, the unit vector. This is really great direction. If I were you, if you were like a highlighting kind of person for certain types of problems that you might need to actually study, you might want to highlight, star, underline, finding the unit vector of u. I'm going to come off to the side just for a moment. Finding the unit vector. If we want to find the unit vector, that means we needed to have a length of length of 1. We need it to have a length of 1. Now the dilemma is with this vector, I can't just put I can't just put j, because isn't this vector, well, u and v, aren't they both tilted? They're not horizontal, they're not vertical. You go over 1, up 5, that's diagonal. You go over 3, down 2, that's diagonal. We need to find the unit vector of specifically u, but he's diagonal, so I can't just use I can't just use j. I need a vector that's going just 1, but in the right direction. Well, I can't really do much until I find what length he currently has. If I need him to have a length of 1, if I need to make a new vector that is the same direction but with a length of 1, well, what length does he have now? Well, how am I going to find what length he has now? The magnitude of vector u is equal to, what am I going to do? Ooh, I need to visualize? I can. Vector u, doesn't he go over 1 and up 5? So isn't this my vector u? You guys agree?
Yes.
How do I find his length? Distance
Distance
formula.
formula.
Or can't I just use Pythagorean theorem? Horizontal vertical will always be 90 degrees, so I can always use my 1 squared plus 5 squared. He is root 26. I need to scale him back to be 1. How do we scale back the unit circle when we had 1, 1, root 2, or when we had 1, 2, root 3? We divided everybody by the hypotenuse. So what am I going to do to my 1 and my 5 if this is right now root 26? Divide everybody by root 26. And if I divide everybody by root 26, I can scale him back to 1, scale him back to, I don't know, and him back to, I don't know. The unit vector for vector u is equal to 1 over root 26i plus 5 over root 26j. Can you rationalize it? Of course you can. But you guys get the idea, right? To scale back the length or the magnitude to be 1, I have to divide. And to divide, well, if I divide one piece to make it a similar triangle, I need to divide all the pieces by the exact same amount. So, to find a unit vector for any vector, we needed to have a length of 1. So first we start by finding what length it currently has, and then we divide each component by magnitude that we found. And then we're done. Now, kiddos, as I said, we do need to take another day on vectors. I apologize, it took a little longer than I thought. But you guys do have your tests close. Yes, you can work in your groups. Yes, you can move around and ask someone specifically. We just need some word problems tomorrow. It's basically the end of section 6.3. Start section 6.3 tonight, for sure, for sure. But the corrections are due tomorrow. So grab them out. Some of you have no corrections. And I think for the most part, you're spread around in different groups. Those of you guys with 100 or over, be available for answering questions. But I do want to see if is there anything where you're like, well, actually pause. Ask in your groups the questions that you have. People that were going to that, so you have a correction sheet. If a group is stuck, let me know and I can help. I have my whiteboard, I have my marker. Pause. You need to be correcting, not talking about the grade. Have you asked your group yet?
Oh no, I want to make it easier.
Oh, do you want to use your squares? Feel free to ask people, but I am available if your group is stuck. I'm right here. No, just the problems. The problems in the bonus, not the formulas.
Do you want to feature these in tomorrow?
You get some done. Because there's no homework due tomorrow because that's just Sunday, so Thursday. Oh, you don't have to question the
Yeah, I use my laptop.
Well, this is Kevin.
Okay.
That's mine.
Give me a second.
So you're like, that's when I could have gotten 100.
Yeah.
Not correcting the formulas, that's just correcting the problems.
What?
And available.
I only need to correct number 2.
You're excited.
With data and 6, and you have to square all of it. You have to square all of it. 5, 10 of that. So that's 10 squared theta. That's 25.
Plus 25. So it's
So
25.
I changed the squared theta to secant
And I just factor
in minus 1. Because then I could distribute 5 and then if you cancel out.
I can't
No, it's not.
And then you have to distribute it, the 25's cancel out, and then it becomes a perfect square. You distribute the 25 down to the secant squared theta minus 1.
We still going on top.
So you take minus 25. And then we do like 5 times.
Yeah, I do.
Yeah.
I have to switch. Oh, you're on top. No, una buena
Oh, that's a
How many percent someone?
Yeah, I'm so confused.
Wait, stop. Do something right. Oh, that's a lot.
So you're right. Turn the 10x into sine over cosine.
I'm right here too. I can answer.
Common denominator.
What? This?
Yes.
That'd be some sine x squared.
No, it's 4 cosine squared x plus 4.
Oh, you guys missed number 2. I'm just gonna put on the board. Yeah. Oh, it's so easy.
Cosine squared x.
It was hard.
Yeah.
It's just like a notes example and a homework problem.
From what?
Oh, wait.
What are you trying to do?
I got
This.
No one's asking me. I'll just do it.
This or that?
So you want cosine of the common denominator.
Patricia, I can't explain this.
It's like hand.
I'm stuck here.
Yeah. And then it becomes 4
Alright, let me teach you how to do this.
I got this to have a common denominator as this, so this becomes 4 cosine squared x. Because you multiply cosine from cosine to this, so it can have a common denominator. Because this is being multiplied, so this already has a cosine.
So this turned into that.
Yeah.
Oh, you literally want something.
Number 2's on board. I went for task, but I know a lot of you missed it. That's probably one of the most commonly missed ones.
Factor out a 4 now?
Just on that? No. You turn the cosine squared of x into 1 minus sine squared. You're having fun. And then you distribute the y.
That cancels out, right?